DSFD called boundary condition. And I think we can start with the first speaker of today, Francesco Marson, whose presentation is titled Enhanced Single Node Boundary Conditions for the Lattice Boltzmann method. Francesco, you can start. You have 15 minutes and then 5 minutes for questions. So I'll let you know 5 minutes before the end with the vocal message.
Okay, thank you.
So please go ahead.
So let me share screen. Okay, normally you should be able to see the screen now.
Yes, yes.
Okay,
yeah.
So welcome to everyone. My name is Francesco Marson, and I am a PhD student at the University of Geneva. Today we'll talk about enhanced single node boundary condition for the Lattice Boltzmann method. This is the outline of my talk, and you can follow it from the top bar. So we propose a new boundary condition for the Lattice Boltzmann method that is local, has a second-order accuracy for velocity, leads to similar accuracy of the Busidi method, that is a well-known method, is easy to implement, and has a quite easy physical interpretation. So the first question is, what do we mean with a local method? So I give to this word two slightly different meanings. The first one is algorithmical locality. That is, if we consider this boundary here on the figure, our algorithm does not need to grab information from other node that is not the node at which we are operating the boundary condition. And then there is the physical locality. That means that in the case in which we had here, for instance, another boundary, our method would be able to operate in this situation in which on this lattice direction we only have one node without doing any special or particular operation. So what is our new method? Well, it's an interpolated bounceback method. The interpolated bounceback are basically an extension of the halfway bounceback method of Lätt. And the idea is that when we have to recover our unknown and time step t+1, that is represented by this population here represented with an arrow. So to recover this information that is missing, what we do is we start from this population at the post-collision step, and then we operate a modified streaming operation. That is, when our population starts the stream, at some point will encounter the wall, and when it will encounter the wall, it reverses its streaming direction, going exactly at the position of our unknown. Now, in general, the interpolated bounceback are an improved version of this halfway bounceback method to be able to handle walls that are not located at halfway between the two, the solid and the fluid node. As you can see, the interpolated bounceback that I generalized here in the linear case also have information from these two populations here, in addition to the Lätt population that we have seen before. Then they combine all this information using interpolation. And so the first question here is, how do we compute this coefficient of the interpolation? There are namely two ways to do it. Either you do use a macroscopic approach to write a closure relation at macroscopic level, and then you use a formal mathematical expansion to find the coefficient. And this method is not what we are going to use for our new method. Or you use a more geometrical approach, getting the interpolation coefficient from a more geometrical point of view. This is what has been done by Busidi and others in the well-known method in 2001. So as you can see, in these two, you have two different cases. When the wall is closer than 1/2 of the internodal distance. In this case, the coefficients can be computed from these two distances, where this point in the middle is the position of the population that is of lattice, at which if we apply the modified streaming that I described before, we would get exactly our unknown at the position xf. that is actually this population here. Okay. In the other case, it's quite similar, but we apply our interpolation instead at the post-streaming step. So before, we apply the modified streaming to this LUD population, and only later we perform the interpolation. In this way, we can compute these two distances, and from these two distances, we can compute the interpolation coefficients. Now, I want you to think now is it possible to make the Busidi algorithm a local method? Because it has a population that is located at node FF at time t. So the answer is yes, because yes and no, actually, because you could think to operate the algorithm after streaming. In this case, the population that was located at FF would be streamed at node F, and if you take care to save the population, the LUD population at node F, then you would have both the information you did located at the XF position. So actually, this is not the ideal solution, because in this way you get only an algorithmically local method. In fact, if you think to have a wall now located between these two nodes, in this case, this blue population wouldn't have any meaningful information inside. So you cannot use it if you want to have a meaningful algorithm. So this eventually causes issues. So how can we solve this problem? So two main approaches have been proposed. The first one that we analyze is the approach of Zhao, proposed in 2017, and it is to perform, let's say, a first-order accurate in-time approximation of this non-local population. So we just take the value at the previous time step. And this is not the method that we choose for our boundary condition. We instead follow the approach of wall population that was introduced by Chung and further developed by Tao in 2010 and Liu in 2019. That is to use some population located at the wall. Let's have a look now to the general formula for our new boundary condition. As you can see, we don't use anymore this non-local population, but instead we introduce these boundary populations. The first one of those has already been used by Tao in 2018. So now we have two main questions here. The first one, what are these boundary population? And second, how do we compute the coefficient of the interpolation? So regarding the population at the wall, we compute them doing a separate evaluation of the equilibrium and non-equilibrium part. For the equilibrium part, we use the standard discrete equilibrium formula, but where we do this approximation here, where we say that the density at the wall is the same as the density at the node F. While for the population, the non-equilibrium population, we use a first-order accurate approximation, either using the Zui approach in an approximated way. This approach was introduced by Chung and Lätt in 2007, or using the regularized approach introduced by Lätt. So why this first-order accurate approximation is enough? Well, as explained by Chung and Lätt, given that our non-equilibrium component is a second-order accurate correction over the equilibrium, a first-order accurate approximation of the non-equilibrium is still enough to get a second-order accurate approximation for the wall population. This was only half of the story. The other half is how to compute the coefficients. So for today, I won't have time to explain it, but I anticipate that in our paper in preparation, we propose a new generalized way to compute this coefficient. And this way will be a visual geometrical way that can also be used to generalize other boundary conditions. Now let's come to the result. The first test case that we performed is a cylindrical co-wet flow, where we have two cylinders that has the same mass. The outer cylinder is at rest, while the inner cylinder is rotating in an anti-clockwise direction with velocity omega. So now we compared our result for the flow inside this blue region, and we compare it with the analytical result. So in these two pictures, you can see the relative root square error, also known as L2 error function, on the y-axis. Instead, on the x-axis, you have the intercylinder distance. That is, basically it's the resolution. So in this figure, you have the new boundary condition that are actually, there are three versions of the new boundary condition. That is the purple, the black, and the gold points. You can see also two sets of results for tau equal, so the relaxation time equals 0.8, and for tau equal 2 in these two sets of results. Then you can also see...
Francesco, sorry, you have 5 minutes.
Yeah, you can also see the red points that are the Busidi method, and the orange point, for who knows, is the U method. And the pink points are the tau method. We can also investigate the viscosity dependence of our new technique, and doing several simulations for increasing relaxation time for different collision models, and we also compute even this time the relative root square error for the velocity field. So again, our results are in purple, black, and gold, and you can see here that we have a pretty resilient behavior at high tau values. And so we have somehow a gain in terms of viscosity dependence of our method compared to the Busidi method in red. Finally, we did a more complex simulation regarding an ellipsoid that is rotating on a shear flow. So you can think to have here two walls that are rotating in opposite directions. And eventually our ellipsoid starts to rotating in this way, performing what is called a Jeffreys orbit. So at left here you can see plotted the angular velocity as a function of the angular position, and you can see that basically our method perform as the other investigated method, and also similarly to the halfway bounceback method at the resolution that we perform, at which we perform the experiment. But this was not what we wanted to check with this experiment. We were in fact more interested on the value of the torque fluctuation, actually the torque square fluctuation, that you can see here pictured in an interpolated way to have a more pleasant figure. And in this case, you can see that the fluctuation of the torque are similar for our new method and for the Busidi and the tau method. Instead, for the halfway bounceback, you have higher values for the fluctuation, and so for the numerical noise. In this experiment, we used the refill technique proposed by Cheng in 2014. So now I will just go through very quickly through the references. You can check it from the recording better, I guess. And with this, I end my presentation, and I thank you for the attention, and I wait for your questions. Thank you.
Okay, thank you very much, Francesco, for your presentation. I think we have time for a quick question, if you wish. Otherwise, we will move to the second talk. Okay, if there are no questions, I will go to the next talk. Thank you again, Francesco, for your presentation.
Thank you for the attention.
And I will introduce the second speaker, Friedman Klaß, who's going to present a talk titled Comparison of Boundary Conditions for Thermal Lattice Boltzmann Method. Please, Francesco, yes, so we can see the screen. You know, you have 15 minutes, and I'll let you know 5 minutes before the end of the talk with a vocal message. So please. Go ahead.
Okay, so first of all, can everybody see my screen and can you hear me? That's maybe the most important question.
Yes. I think we can.
Excellent. Okay, so hi everyone, welcome from Wuppertal. I'm a PhD student there. My name is Friedemann Klaß, and I'm going to talk about a comparison of boundary conditions for thermal lattice Boltzmann models. And in fact, I'm going to be a bit more precise here because we are going to consider high-order lattices and boundary conditions for high-order lattices, which offer one way to simulate a fluid that evolves according to the Navier-Stokes Fourier equations eventually. And you see here the two most common, basically two-dimensional velocity stencils, namely the DQQ17 velocity stencil for mildly compressible flow and the DQQ37 velocity stencil for fully compressible flow. And the motivation behind considering high-order velocity stencils is basically that this has been shown to lead to an increasement in stability with respect to temperature range and velocity, viscosity limits, and so on. This has been done in a paper by Siebert and co-workers. However, as you can see, we have multiple speed levels here, and therefore we have multiple boundary layers. Therefore, we have a more complex multiple boundary treatment, and we can endanger this gain in stability basically by formulating poor boundary conditions, and this serves as the motivation for this work. Just very quick, the model we were using, as you have seen, the DQQ17 and DQQ37 lattice, and they come equipped with the third and fourth order Hermite expansion of the equilibrium distribution respectively. And we are going to use the easy single relaxation time BGK collision operator with a Prandtl number of 1 essentially. And we are using the shifted equilibrium formulation here to incorporate an external force. Yeah, details for this can be found in this reference here by Scagliarini. Yes, now turning to the boundary conditions for the stencils we consider here, we have three speed layers depicted, and here are depicted the unknown post-streaming populations in each layer. For the DQQ37 stencil, again for the DQQ17 stencil, this will look very similar. And we are going to discuss the well-known diffusive boundary condition, a modified equilibrium scheme, and a new thermal extension of a multi-speed non-equilibrium bounceback approach. So the diffusive boundary condition is, I think, well known. Here, what is the basic assumption? The basic assumption is that you have a non-absorbing wall that causes diffusive scattering on reflection, which has been developed by Andromali and Carlin, and this also preserves the non-negativity of the incoming populations. And this has been extended to multi-speed lattices by Meng and his co-workers, where the essential idea basically is that you keep track of incoming and outgoing velocities layer-wise, and then eventually you can set your unknown post-streaming populations according to this formula. So this is all known, and behind this modified next boundary condition, the modified equilibrium boundary condition, there's a bit of a story here. So the basic idea is that you impose temperature and velocity at the boundary, and since you have more unknowns than constraining equations, you tie the unknowns together by the following ansatz. You set for each unknown population Fi, you set them as phi I multiplied by some scaling factor here, and the phi is given as some term mimicking a low-order equilibrium expansion, basically in the unknowns P and E. And the N is the constant that is basically responsible for obtaining mass conservation in the end, because if we set N to the outflow out of the computational domain, then obviously we will just redistribute this outflowing mass to the unknown populations. And plugging this into the temperature and momentum equation, we can solve for the unknowns P and E. So we have D+1 equations and D+1 unknowns and the closed system, therefore. However, this system has the purely mathematical property of having potentially negative solutions, and thus we can set negative populations, and they may even propagate. And we have seen in our benchmarks that for relaxation times that are not 1, we couldn't even reproduce a simple quad flow, for instance, with this boundary condition. So we resorted to the case tau equals 1, and as you can clearly see, this will just reduce to an equilibrium boundary condition in this case, since the mass conserving density is known, and this is also the main point of the modification. You just set the density to the mass conserving density. So you can also think of this as a mass conserving equilibrium boundary condition. And now turning to the non-equilibrium bounceback approaches, famously for isothermal single-speed models, this has been introduced by Zhu and He. And Martin Hecht and his co-workers extended this to other velocity stencils than DQQ9 basically, and the main idea was that they take this non-equilibrium bounceback approach here and also introduce velocity correction terms that they scale with, the Kate correction term will be scaled with the Kate velocity component of the respective unknown lattice velocity, and then you can compute this equilibrium here with respect to an imposed velocity. They also call this on-site velocity boundary condition and an obviously unknown density, and then again you end up with a closed system. So far, so clear, I hope. And you can easily extend this actually to multi-speed lattices in the isothermal case, which has been done just recently by Lee and co-workers. And as you can see, the formula looks basically the same. The only difference is that you have to keep track again of the unknown populations in the unknown in the boundary layers respectively. And they also did this conceptual tweak of introducing this factor M here, which is basically either 1 or the lattice wide. And they call this the scaled or unscaled version of this boundary condition respectively, because the motivation behind this was that the scaled version would lead to a lower numerical viscosity, which was a reported result in the original paper where they proposed this boundary condition. And before we give a thermal extension, we briefly discussed another binary choice, basically, they discussed in their paper. So you have this choice to make if you want to have an internal or external population replacement. As you can see here, in the external population replacement, you treat basically all boundary layers the same. And for simplicity, this is what we will focus on, because this will lead to, basically not 3 systems of equations you have to solve, but 1. As an alternative, you can also do the internal treatment, where you only substitute the missing populations, and the macroscopic values to be imposed here on the next to the boundary layers will be obtained via interpolation. However, depending on your underlying velocity stencil, it may be that you don't have enough degrees of freedom here in the innermost layer. So from this point of view, this isn't even general enough. So this is another reason for considering the external population treatment, actually. And we now give a pretty straightforward extension to the thermal case, actually. What changes in this case is that we have an additional equation to fulfill when we also impose a temperature. And what do? We also introduce an additional unknown, which we just consistently label a temperature correction term Qt, which we scale with the absolute value of the missing lattice velocity. And apart from this, the ansatz looks basically the same. And obviously, the idea is now that we solve now the momentum and temperature equation for these correction terms. And a bit of a technical slide here. We distinguished several schemes, which here we labeled scheme 1 and scheme 2, and both of them have this unscaled and scaled version evaluated later on. So we will label them U1 and S1 respectively, and the same for the second scheme. And for the first scheme, the idea is that you drop the correction and the equation for normal velocity from your system of equations. The reason for doing this is that density and the velocity are linked by the continuity equation, and therefore the normal velocity is determined when everything else is fixed, and everything else will be fixed by solving, imposing the different velocities and the remaining velocity, and then solve just the remaining d+1 equations in d+1 unknowns, where d again denotes the dimension. And in the scheme 2, we actually try to enforce a no-slip boundary condition, where we just express the density in terms of all the unknowns and then solve the full momentum and energy equation, and then have correction terms and the correction terms for velocity and temperature. So we again only consider closed systems here. But by doing so, however, we violate the continuity equation, and in both schemes, actually, we will not be able to conserve the mass of the system in general because of some outflow, because of a kind of arbitrary density from the continuity equation's point of view. And therefore, we face this trade-off of either conserving all the mass in the population, in the system, or to impose an exact temperature, because we can kind of save this lack of mass conservation by modifying the rest population, which is kind of a default trick, basically. But in doing so, we also alter the imposed temperature at the boundary, at least for non-moving walls, as you can see by the definition of the temperature equation. This lack of mass conservation motivates us to kind of merge the ansatz for the non-equilibrium bounceback with the ansatz from the equilibrium boundary condition we have seen a few slides ago. So basically our new ansatz now looks like this, and by construction again this will be mass conserving if we choose n as the outflow of this node. And we again resort to solving the momentum and energy equation for the correction terms. However, we are not able to do this in the pre-processing step, as it was the case with the other boundary conditions, so we had to resort to numerically solve this on the fly in each iteration, which leads to a very expensive scheme. And we label this num for numerical solution here. However, we expect that while this is expensive, this should also be more accurate than the other non-equilibrium bounceback boundary conditions presented, since we circumvented this mass-conserving problem.
Oh, Friedman, you got 5 minutes.
Okay. And now turning to the numerical results, the first thing we considered was the thermal quet flow. Pretty standard, I think. Now the top plate is heated and the bottom plate is cooled. Also, this flow has the nice property of having analytical solutions for the velocity and temperature fields, respectively. And therefore, we can do the following. We can just consider some steady state L2 errors in the velocity and temperature fields. And this is what I'm showing you here on the next slide for the L2 error in velocity. So here you see basically a small grid convergence study at a fixed Reynolds number of 100 and several Eckert numbers, namely 110 and 100. And you see all this basically the zoo of all the different boundary conditions from the non-equilibrium bounceback approach. But it may be a bit hard to read, but the main takeaway here is that for this moderate to low Reynolds regime, we see a clear gain in accuracy from this non-equilibrium bounceback family of approaches. And they are a bit superior to the diffusive boundary condition and equilibrium boundary condition here. And we also see that our expectation basically holds true, that we have a lower bound basically from the numerical boundary scheme here. And also for the other Eckert numbers. And we also see that we have about second order convergence in terms with respect to the velocity, which is quite nice. And for the temperature field, however, we somehow lose this advantage for most of the schemes, but this numerical scheme still forms a lower bound, as you can see here. And maybe the more interesting point is that we were somehow not able to obtain second order convergence here in the temperature field, but we only, as you can see, have only about first order convergence at all the different Eckert numbers. So this is something we could maybe discuss after this talk, possibly in 1 or 2 minutes. The next and final benchmark we considered was basically a stability test in the Rayleigh-Bénard convection. So what we did is we considered the DQQ17 and DQQ37 stencil at several fixed temperature jumps with respect to the reference temperature here. And we kept the grid and acceleration fixed and effectively tuned the Rayleigh number by altering the viscosity. And as you can see for the DQQ17 stencil, we have a similar performance for the diffusive and equilibrium boundary condition, while the non-equilibrium boundary condition is clearly very, very inferior and can't even reproduce the critical Rayleigh number of the simulation, basically. The situation increases a bit and gets a bit better when we turn to the fully compressible DQQ37 stencil. Then pretty much every simulation has gained some benefit from this, but also still we have more than 2 orders of magnitude difference between the highest Rayleigh number attained for the non-equilibrium bounceback and the other boundary conditions. And this is sadly a negative result. And also what's still an open question is, why is it that this non-equilibrium bounceback doesn't seem to benefit at all from reducing the temperature jump? It seems like there is something inhibiting basically the stability at this point here. And yes, this can also be seen actually as maybe an advocate for the stability of the equilibrium scheme, surprisingly. And this brings me to the summary, and then I think I'm also out of time. We have seen that the equilibrium and diffusive scheme are very robust and what's also true is that they are very simple to adapt to different stencils. I mean, equilibrium is obvious in the diffusive boundary condition, just the sets that you have to keep track of alter, while for the non-equilibrium bounceback approach, you have to redo all this pre-processing of coming up with a solution of a complicated system of equations for each stencil. However, this can give superior accuracy, at least in low Reynolds cases, but this is very expensive and it also supports only a narrower range of parameters, which kind of defeats the purpose of going for higher order stencils in the first place. However, maybe one can save this by maybe choosing a smarter ansatz for this non-equilibrium bounceback term. You remember we only put the absolute value of the lattice velocity times the temperature correction term in there, and who knows, possibly there is another better way to do this. And now I would like to briefly show you my references here, and this is pretty much it. Thank you for your attention and feel free to ask any questions.
Okay, Friedman, thank you very much for your presentation. I think we had time for a couple of questions. So I think Luis Segele has one. So
Can you hear me?
yes.
Yes.
Okay, Friedman, thanks very much for a very nice presentation. I would just like to ask you if in your thermal quet flow, you have showed us the error, right? What about the profiles? Do you have any? How is your temperature profile especially at the wall? Do you have any jump or in the profile of the temperature or the pressure? Have you measured that, or can you show us some result regarding this parameter?
So I maybe don't have any plots at hand currently, but maybe I can answer at least a few parts of this question. So it is indeed the case that for the equilibrium boundary condition, well, obviously, depending on the configuration of the flow, you will have some jump at the boundary, especially in the temperature. And this was very much alleviated basically by the diffusive boundary condition, but I can't spontaneously be more precise on this, sorry. And was there a second part I didn't answer so far, or was that everything?
So it's also about it's about the pressure because you have to choose whether if you're conserving or mass or temperature, right?
Okay.
So perhaps you're gonna have a jump in the pressure. So possibly you're gonna get a wave, a pressure wave coming from the wall. So that's my point.
So this could also maybe explain the lower order convergence if we somehow modify in a non-physical way the mass to obtain mass conservation, yes. But no, I don't have any figures for this currently.
Yeah, no problem. Thanks very much for your presentation.
Thank you for your question.
Okay, thank you, Luis. If there is another question, I think we have 1 minute. Okay, if there are no more questions, there is coffee break now. So we got 20 minutes stop, and then we will be back for the next session of talks. See you in 20 minutes at 11:20. Thank you for your participation. Thank you again, Friedman. Boundary conditions for cascaded and cumulant CO-based lattice Boltzmann shallow water models. Sarah, yeah.
I'm here.
Yeah, okay.
I present. Wait.
Okay, it's loading, yeah.
Do you see the presentation?
Yes.
Yes. Okay, good morning, everyone. I'm Sara Venturi, and I work at the University of Perugia. I'm going to present the work titled Boundary Condition for Cascaded and Cumulant Collision Operator-Based Lattice Box Shallow Water Model. In this presentation, a brief overview, I'm going to present, to illustrate two innovative models, two innovative shallow water lattice Boltzmann model, the MRT cascading model and the MRT cumulant model. Then I'm going to present the boundary condition that I used, that we implemented in our model. In particular, I do a comparison between two different types of inflow-out boundary condition, the Zue boundary condition and the non-reflecting boundary condition. Finally, I'm going to present a strategy in order to simulate a wet and dry condition at moving boundary and its validation and an application to a case study. The lattice Boltzmann model is a mesoscopic bound model in between microscopic and macroscopic continuum model. And it consists in two main steps, the streaming and the collision. During the streaming, the particles move in the direction of their velocities toward their neighboring nodes. And during the collision, the particles collide into each other, conserving mass and momentum. The shallow water model is based on shallow water equation. It's a two-dimensional model in which the momentum is substituted along the vertical by an hydrostatic distribution of the pressure in order to obtain quantities that are averaged along the vertical, in particular the water height, the water depth and the velocities along the horizontal plane. Our model is a lattice Boltzmann model solving shallow water equation. Is a D2Q9 model, so we have 9 direction and 9 velocities. The lattice pattern is shown in the slide. In our model, the macroscopic variables can be obtained by means of raw moments of the distribution function, in particular the water depth by the zero order moments and the velocities along the horizontal planes by the first order moments. In one of the main differences of shallow water lattice Boltzmann model from the traditional lattice Boltzmann model is that the speed of sound is not constant, but depends on the water depth, as is possible to see from the equation highlighted in yellow at the bottom of the slide. This in order to respect the conservative form of shallow water equation and the equation of state of the flow. Then put our attention to the two innovative models for shallow water equation that are the first of the models taken into consideration is the cascading model. It's based on the use of central moments that are quantities that are Galilean invariant by definition, and the collision step is performed in terms of central moments, and in the slide we can see the values for the equilibrium central moments. In our model, the relaxation rate that are related to the viscosity are the ones connected to the second order moments, in particular the omega 1,1 and the omega 2,0 and 0,2. Recently, in a recent work, in this model was implemented a procedure in order to take in account the external force, and this procedure was successfully validated with traditional benchmark test cases. The second model is the cumulant model. Cumulants are observable quantities that are Galilean invariant and statistically independent by each other by construction, and the mathematical formulation of cumulants can be found in the work of Geier. In this model, the collision step is performed in terms of cumulants. Cumulants can be obtained by central moments, this until third order. For moments for higher order moments, we can use the formula highlighted in yellow at the bottom of the slide. The cumulant model, in a recent work, the cumulant one, it was shown that the cumulant model maintains a correct viscosity with second order convergence, overcoming the stability problems of the traditional approach to shallow water by means of Lattice Boltzmann model, that is the BGK, also for low values of the viscosity. Then the boundary condition. We can say that surely boundary conditions play a critical role on accuracy, efficiency, and stability of the simulation. In our model, different boundary conditions have been implemented: the standard boundary condition, periodic boundary condition, solid boundary condition. For example, there's no slick boundary condition that is based on the bounceback method. In the picture, the halfway bounceback method that is implemented in our models, and then the inlet-outlet boundary condition. In particular, I'm interested in comparing two different types of boundary condition that are the Zue boundary condition and the non-reflecting boundary condition. The Zue boundary condition are based on the conservation of mass and momentum, and on the bounce back rule of non-equilibrium part of the distribution function at the inlet and the outlet section of the channel, for example. And as we had to adapt this boundary condition for our innovative model, so we obtained a new type of boundary condition that, yes, for the inlet and for the outlet, we can see them at the bottom of the slide. And so we had to validate this boundary condition by means of standard benchmark test case, one-dimensional and two-dimensional. The first is the steady flow over a bump, and as we can see from the slide, we had a good accordance between the analytical solution and the numerical solution. In particular, as expected, the accuracy increases with the decreasing of the grid spacing. Then, going ahead with the 2D validation, we used the flow, the Poiseuille flow in a channel. As we can see from the graph at the bottom of the slide, there is a good accordance between the analytical and the numerical solution at section A, at the middle of the channel, for all the grid spacing considered. Then for this test case, we performed a convergence analysis, and in particular, we can see that the model exhibits a second order accuracy with the increasing of the resolution. Then, as I said before, I want to compare, in particular at the outlet, Zue boundary condition with non-reflecting boundary condition. These boundary conditions are based on a linear interpolation between the distribution at the outlet and the distribution from where the pressure wave comes from. In particular, in order to do this comparison, we took into consideration a simple simulation. We observe the wave due to the velocity wave in two models. The first, the one defined by the orange dot, use the Zue boundary condition. On the other side, the one using the non-reflecting boundary condition is defined by blue dots. As we can see, as we can see, the wave due to a perturbation of the water surface when the flow bump into the wall is too higher. The wave due to the reflection of the wall is 2 times higher when we use the Geier boundary condition. Going ahead with the presentation. Now I'm going to explain the procedure implemented in our model in order to.
Sorry, Sarah, you have 5 minutes.
5 minutes, okay. In order to model the propagation of a wet-dry front. It's we can see on the left of the presentation the flow chart of the implemented procedure, and this procedure is based on a double limiter, a limiter on the height of the water and a limiter on the velocity. When about the limiter on the 8, when the 8 is higher than the limit, we impose the distribution function equal to 0 and the water depth equal to the limiter. About the velocity limiter, the velocity, as we can see from the equation highlighted, the velocity is limited by a factor equal to the ratio of the limit value of the Freud number and the actual value of the Freud number. In order to validate this approach to model wet and dry front, we use the benchmark test case by Soares-Frazao, and we compare the Lattice Box shallow water model based on a cumulant collision operator with a continuum two-dimensional model. We can see that the agreement between the two models is good, especially at first times. Then at time 3.5 seconds, we can see that they are slightly different because the continuum model presents a crest higher at the downstream of the obstacle. Then we use the model with this routine to model wet and dry front in a real case study, the Malpasset-Dambreck. In the slide, we can see the localization of the Malpasset-Dambreck, and a DTM where are reported the field data available for this case study. In particular, the electrical transformer A, B, and C, where we have available the arrival time of the flood, the point PE measured by the police, where we are available the water surface and the velocity, and some points named G, where we have available the water surface and the arrival time due to a physical model by EDF. Then, going ahead briefly with the result, we can see that we have a very good accordance with the arrival time measured during the event at electrical transformer A and C. Then comparing the water surface measured at P points with the water surface measured by the numerical model, we can see that there is surely a good accordance. The error obviously depends on the grid spacing used, is about 5% if we use a grid spacing of 20 meters, and about 4% with a grid spacing of 10 meters. It's interesting to note that result in literature due to Valiani present a medium error of the point higher, about 8%. About G point by physical model, we can see there is also in this case a good accordance, and the medium, the error for all the points considered is always lower than 10%. In the last slide, we can see for picture for different time of the simulation. We can see how the flood propagated in the Reiran Valley. It's possible to note that this propagation is in accordance with the event records during the event. The conclusions. So we illustrate a different type of boundary condition used in our work. These are the standard boundary condition, but in particular we performed a comparison at the outlet for the outlet boundary condition between the Zue boundary condition and the non-reflecting boundary condition, and we note that effectively as expected, using the non-reflecting boundary condition, we have a decreasing in wave reflection. Then we explained the strategy in order to simulate a moving boundary in the propagation of wet and dry front. A boundary is a strategy that is based on a double limiter, on the depth and on the velocity. And we found that we had a satisfactory result in test case and also in a real case study. And I finished. Thank you.
Thank you very much, Sarah, for the presentation. So I think we have time for one or two questions, if there are any. Okay, so if there are no questions, I would say that the session is over. So I would thank again all the speakers for their beautiful presentations, and so all the participants for coming along. And so we can move to the plenary session where there is in 20 minutes, I think, a tutorial by Bogosian about new developments in kinetic theory of wealth distribution. So see you in 20 minutes in the other room. Thank you all again.